Good morning, everyone. So we're going to pick back up here in chapter 4 today. So we'll get through probably about section 4.3, maybe a little bit into 4.4 today in the chapter. We'll probably come pretty close to finishing chapter 4 Wednesday. We'll do some review of chapter 4, wrap chapter 4 up on Friday, maybe touch a little bit of chapter 5 on Friday as well. In terms of our next exam, it's not next Tuesday, but the following Tuesday. So we get all of this week, all of next week for lecture, and then Monday before. And we're going to go through most of chapter 5. We're going to go through section 5.7. So we'll talk about midterm 2 as we start getting a little bit closer. But just in the back of our mind, we're about 2 weeks away from midterm 2. And so the next topic, or the topic we're going to talk about here, is precipitation reactions. So when we combine solutions of compounds that are salts, think of ionic compounds. And so also remember, if you have a soluble ionic compound, that it's ionized. So it's going to be in solution as the ions of that ionic compound. So when we mix solutions, like imagine mixing potassium iodide, so Ki is water soluble. Anything with potassium is water soluble. Most iodides are water soluble. Potassium is not one of the exceptions. So this is an AQ, meaning it's K plus and I minus in solution. And so then we can also have a solution like lead nitrate. So you can buy lead nitrate in solid form, add it to water, and it'll dissolve. And then it releases lead ions and releases the nitrate ion. So if you can think about naming, if you can name the ions, this is lead nitrate, it releases lead 2 plus, releases the nitrate ion into solution. And so a solution of lead nitrate kind of just looks like having lead and nitrate ions, just in a ratio of 2 nitrates for every 1 lead ion. And then we can mix these two solutions together where we have the solution of potassium ions, iodide ions, nitrate, lead ions. We also have water molecules present in this solution. And so then if we can form a solid precipitate, if you mix these together, you do this in lab. This is like the PBI lab. Have you guys done that lab? Yeah, okay, it's coming up soon. But you kind of synthesize, or you can synthesize this compound in lab by mixing the two solutions, and then we form that solid precipitate. Why do we form a solid precipitate? Well, lead forms an insoluble iodide. So PBI2 is insoluble in water, meaning the ions don't stay in solution, but they collect together. They form an ionic compound where we have the alternating plus minus all throughout the structure. And so then that's the yellow solid that sinks to the bottom of the test tube, sinking just because the ionic compound has a greater density than the solution. And that's usually the case. Most salts are going to be heavier than water. They're going to sink to the bottom of our test tube. And then we're going to separate those from the ions that remain dissolved above the solution. We can then write out a reaction like Ki, AQ meaning water-soluble compound. So the AQ here, so we're looking at this being an ionic compound. This is using the solubility guidelines. So if it's soluble, if the answer is yes, then it's AQ. If it's not soluble, then it would be a solid. And there's a big difference. We might write KiAQ, but it's not Ki in solution, it's K plus and A minus in that solution. Lead nitrate's really Pb2 plus and 2 nitrate ions, because it's also water soluble. And so then our products here, KNO3 is the water soluble product. So we're just kind of swapping out these ions here, and then noticing that when we put the iodide with lead, that it's insoluble. So then we have PBI2 solid. And this is what drives this reaction to take place. So the formation of solid is what allows us to have an actual reaction take place here, because we're forming that solid and then that separates from the rest of the solution, allowing this reaction to take place. So we'll see an example in a minute where if we don't have a solid, if we have AQs in every spot, if we have 2 aqueous salts producing 2 aqueous salts, that's actually not going to be a chemical reaction. We'll try to see why that is here in a minute. So for this reaction here, we're sort of thinking about the solubility guidelines to figure out the solubility of our salts before the reaction and after the reaction. And then metathesis or exchanges, we're just exchanging the ions with each other, exchanging the 2 minus ions in which plus cation they're paired up with, and seeing if we form an insoluble compound. So how do we predict if there's a precipitate formed when solutions are mixed? So generally speaking, if we're mixing solutions, they're already soluble, because that's what it would mean to have a solution to begin with. So if we're mixing aqueous solutions, let's imagine we're mixing magnesium nitrate and sodium chloride for a moment, that those are the two salts that we're mixing together. MgNO3, as one of our reactants, is at water soluble. All nitrates are water soluble, so that's an AQ. And then for NaCl, all alkali cations are water soluble. And then almost all chlorides are soluble with 3 exceptions, so of course sodium's not one of them. So that's an AQ. Sodium chloride certainly in solution. And then magnesium chloride. Magnesium's not one of the exceptions for chloride, it's just silver, lead, and that goofy Hg2 2+ ion. So this is an AQ. And then sodium nitrate, NaNO3, all nitrates are soluble, all alkali cations are soluble. This is also an AQ. So what we want to find is we want to find a precipitate in one of these two spots. We want to find something that's water insoluble. And if we're AQ in both, then what have we really done? We've just really mixed solutions of ions and led to a solution of ions. We haven't really changed the chemical nature of the two solutions when we mix them together, when we only form two aqueous substances. So we want to try to find a precipitate. The next slide will kind of look at an actual reaction to show that there's actually no chemical change taking place in this reaction since there's no solid being formed. And so we want to note the ions present in the reactants. Water soluble is aqueous, water insoluble compounds we'd write as solid. Everything in this reaction here is aqueous, water soluble. And then we want to consider the solubility chart to figure out if we have an insoluble salt. We did that. We didn't have one here. So let's take a look at the next slide, which is going to try to break this reaction down into an ionic reaction. So we can go from what we call this reaction here is what we call a full molecular reaction, or it's trying to write this reaction as if it's molecular, like kind of in quotes, meaning magnesium nitrate is not MgNO3 in solution. It's magnesium ions and it's nitrate ions. So if we want to write MgNO3 AQ, this is almost like in quotes, right? Because we have to think this compound here is a strong electrolyte because it's an ionic compound, because it's water soluble. All these three things kind of together would tell me that in solution, MgNO3 is really magnesium ions, aqueous, and then nitrate ions, just in that ratio of 1 to 2, 1 magnesium for every 2 nitrates from the formula of the compound. That's also taken into account from the name magnesium nitrate tells me nitrate stays together. It's not going to dissociate into like nitrite or oxide or anything like that. And then sodium chloride. I'm just going to take into account my 2 in front of NaCl from the balancing. So I have 2 sodium ions, 2 chloride ions, because sodium chloride is a water-soluble ionic compound that therefore has to be a strong electrolyte, meaning it ionizes into sodium and chloride ions completely. So what we're doing here is we're ionizing our strong electrolytes. So if I have a strong electrolyte, an electrolyte is something that ionizes. Strong is complete ionization. And so I ionize the sodium chloride. And then because both of my products are water soluble, they're ionic compounds, they're also strong electrolytes. So my strong electrolytes fully ionize in the products. So I have magnesium and chloride ions. And then in the case of NaNO3, sodium and nitrate ions. So from the full ionic reaction, I think you can see, hopefully you see this, that we have the same ions on the left side as we have on the right side. So if you go back to chapter 1, is there a chemical change that took place during this process? There's no actual chemical change. We're just mixing solutions of ions together and kind of like diluting them in each other. So we're just doing kind of a physical reaction here. We're not really doing a chemical reaction. So there's no chemical reactions taking place because there has to be a net change. There has to be some sort of net chemical change. A chemical change would be forming an ionic compound that's a solid that precipitates and leaves a solution, so that we're going to form that new ionic bond between those cations. So seeing a solid form is going to be a requirement here for this reaction to take place. So here there's no net change because there's no chemical reaction taking place. We're seeing everything's what we call a spectator ion. The spectator ions are the ions that are unchanged during the chemical reaction. And so ions that are unchanged, we can sort of imagine canceling out the unchanged ions. And here we're just canceling out the entire reaction in terms of the net change. So I'm looking for what's the net difference on the left and right side. There is no net difference. So no reaction here because all the ions turn out to be spectator ions. Now let's obviously contrast this with the reaction that leads to precipitate formation. We could use the lead nitrate example, but let's look at a reaction of magnesium nitrate and sodium hydroxide. And so magnesium nitrate, MgNO3 as before, AQ. Anything containing sodium is water soluble because it's an alkali cation. It's of course a listed exception for hydroxide ion, so we know it's water soluble, it's an AQ. And then magnesium hydroxide. Now, if you look in the solubility chart for hydroxide ion, we see that the exceptions that are soluble are the alkali cations, but in the alkaline category, it's just calcium, strontium, barium. Doesn't include magnesium on that list. So the implication here is that MgOH2 is a solid, insoluble. So we can check our solubility chart. You can use that on tests, so if you're wondering if you have to memorize the solubility chart, you don't have to memorize it. You just have to know how to check it and how to understand how to use it. Most hydroxides are insoluble. The exceptions listed are soluble, and this isn't a listed exception. NaNO3 is an AQ because, of course, sodium and nitrate both are always soluble without exceptions. And so if we're thinking about the net change here, we can probably start to see the net change is going to be the formation of that solid precipitate. So forming that solid is really what drives these precipitation reactions to take place. You can also think in the category of name of reactions, it's called a precipitation reaction for a reason, because we have to form one of these insoluble precipitates. So this would be the precipitate that forms in the reaction. The solid, the insoluble compound, is that precipitate. And so then let's think about writing reactions that can take place. So the full molecular is one we just wrote. The full molecular is the one where it's like, just write these substances as if they're molecular. Like NaOH is not sodium hydroxide in water. In water, you don't have the sodium and the hydroxide stuck together anymore. You really have the sodium ion and the hydroxide ion. And so we're thinking here strong electrolyte. If it is a strong electrolyte, we dissociate it. And strong electrolyte just means the compound fully dissociates in water. And so then magnesium nitrate does this. It's a strong electrolyte. Now, what about MgOH2 solid? Is that a strong electrolyte? Does it ionize in water? No, it can't, because it's solid. It's sitting at the bottom of the test tube as the precipitate. So this compound here is not a strong electrolyte. Because it's not a strong electrolyte, I have to keep it stuck together. I have to keep it intact as MgOH2 solid on the product side. And then my NaNO3, this is of course a strong electrolyte. So I have 3 strong electrolytes that I'm circling that fully dissociate in the solution. So we can dissociate them in what we call the full ionic equation or the full ionic reaction. I don't know why the book calls reactions equations. It kind of bugs me a little bit because I don't know. I like to think of these as reactions, not as equalities, because it's not that the reactants equal the products, it's that the reactants turn into the products. But anyways, the book calls this either the full ionic equation, or I think of it as the full ionic reaction. And so then we can then say, or think about which ions are the same on both sides of the reaction. Those are our spectator ions. So the spectators are the unchanged ions. They're the ions that like watch the reaction. Now when I do this, when I cancel out the spectator ions, they're not disappearing. They're not unimportant. They still need to be there. They're just not part of the net change. So if I'm looking for the net reaction, I just cancel out the unchanged parts of the reaction. So the net change, we call this the net ionic reaction or the net ionic equation. The net reaction just meaning, well, what's the actual change that's going on in the reaction? Well, the actual change is Mg2 plus AQ plus 2 hydroxide ion AQ form MgOH2 solid. That's the net change. So the spectator ions are neglected from this equation because they're not part of the net change. They're unchanged during the course of the reaction. Okay, so we can identify spectator ions because they're the ones that are unchanged in this process. We can identify the net change. If we can identify a net change, then we know a reaction took place. So if we said, does a reaction occur when you mix magnesium nitrate and sodium hydroxide? The answer is yes. The net reaction that would take place is that precipitation reaction. If we had the previous example, if I said, is there a net change that takes place between the mixing of magnesium nitrate and what was it, sodium chloride? The answer to that one would have been no. There's no net change because we didn't form a precipitate. We didn't form any actual net change. So then a question here. Let's think about this. Let's actually do this together. There's a couple questions maybe we'll do towards the end for the lecture activity for today. Let's think about this question here. Which solution, when mixed with a solution of barium nitrate in water, yields a precipitate? So we have barium nitrate. All nitrates are water soluble. So we're thinking when I mix it with a compound here that's listed, which one gives me the formation of a solid precipitate? And I'm always going to have a second product that's usually an AQ compound. Let's think about A. So if we go with A, we go calcium acetate. So calcium C2H3O2, 2. This is the acetate ion. So that's an AQ because all acetates are water soluble. So I think you can probably see here this isn't going to lead to a net change, right? Because all nitrates are water soluble. All acetates are water soluble. Neither one of them have any listed exceptions. So if we imagine switching out the ions, if I imagine trying to form barium acetate, then I imagine trying to form calcium nitrate, this is not a solid. This is an AQ because it's water soluble. So when I go with answer A, I get water soluble plus water soluble. No net change occurs when we mix calcium acetate with barium nitrate. Now lead, answer B, you see lead, you're like, okay, it's got to be answer B, right? Because we see lead forms insoluble compounds, but does lead form an insoluble acetate? No. And so if you notice, the ion in B is also acetate. So if we switch nitrate and acetate, we'd form lead nitrate and barium acetate. Both of those compounds are water soluble. So even though I see lead ion, it doesn't mean that's going to be the answer to the question because I have to get an insoluble compound when I switch out these ions. I switch those ions out, I still have 2 water soluble compounds. What about answer C? Does C work? It looks like it might because hydroxides are mostly insoluble, but barium hydroxide is water soluble. That's one of the listed exceptions for hydroxide. And so then if we switch the potassium for nitrates, we get KNO3. That's also water soluble. So the products, when I mix KOH with barium nitrate, I get 2 water soluble products, not an insoluble product. So hopefully it's D. And it is D, right? Because barium sulfate's insoluble. So let's write that reaction out real quick. So let's even go through the process of saying, for D, can we write out the full molecular reaction? Can we write out the full ionic reaction? And then can we write the net ionic reaction? And then can we identify and cancel out those spectator ions in the process? So let me erase this work here to give me some room to write. And so, again, we're taking our 2 reactants, barium nitrate, which is water soluble, so let's throw an AQ on there, K2SO4, also water soluble. So it's our solubility chart. We're going to sulfate and saying, does barium form an insoluble compound? Is BaSO4 water soluble? Remember, sulfate's a 2-, barium's a 2+, so BaSO4 is our solid precipitate, because that's insoluble in water. And then our byproduct's going to be KNO3. Water soluble. If we want to balance, we're going to need 2 KNO3s. That gives us 2 potassiums both sides, 2 nitrates both sides, and that puts us into balance. So that's all we needed to do to balance the reaction. So this would be our full molecular reaction. And then the net ionic, just try to think about how these things actually look in solution. Think about how these are all ionic compounds, and if they're water soluble, they fully ionize. So the AQs are fully ionized. So we'd have barium 2+ plus 2 nitrate ions. I'm going to neglect writing AQ every time for an ion. I know it's surrounded by water, so all our ions are AQs. I'm just going to neglect writing the AQ tag. So I have a water-soluble K2SO4, so 2K plus SO4, 2 minus. So I'm just trying to take into account and not lose track of my coefficients here. And then BaSO4, this is the main point here. Sometimes we forget about this, or the whole idea is that we're not dissociating any ionic compound, we're just dissociating the water-soluble ionic compounds. So an insoluble compound is not a strong electrolyte. So BaSO4 stays as BaSO4, 2K plus 2 nitrate ions for the KNO3. And so then what are the ions that are unchanged? The unchanged ions are the nitrate, and the K plus and the K plus. So we want those ions to be in exactly the same form on both sides of the reaction, and they are. So we can cancel them out, and we write the net change. So our net change is going to be barium 2 plus. We can throw the AQ if you want to make sure to see it in there, that these are all AQs, the ions, and then we're forming BaSO4 solid. This is our net ionic equation or reaction. And again, the first reaction we started with was our full molecular. I like to think of molecular on quotes because it's kind of like writing it as if the reactants are and products are molecular, as if they are stuck together. It's a very common way to write reactions and think of them. We just have to remember strong electrolytes fully dissociate. And then our spectator ions, of course, are the K plus and the nitrate. So it's very common for the ions that are always soluble to be the spectator ions in the reaction. It's very common for the ions that are precipitated, like sulfate, to be the not spectator ions, or the ones that are actually part of the net change. So that's how we can predict when a reaction occurs, how we can see when reactions don't occur, how we can then write reactions that go along with these reactions and hopefully understand the difference between full moleculars, net ionic, and spectator ions. Okay, so let's get back into acids and bases. When we did that activity on Friday, we were demonstrating some properties of acids and bases and kind of seeing for acids and bases that we are seeing categories of compounds that could be either strong or weak electrolytes. And the word weak electrolyte for an ionic compound almost doesn't even come up, because an ionic compound where we have metal, non-metals paired together, that it either dissolves in water and dissociates completely, or it doesn't dissolve in water at all would be the implication. So for ionic compounds, the salts, the ICs, are either insoluble or strong electrolytes. But we're going to see for molecular compounds that you can have a range of electrolytic behavior. We're going to see we have weak acids, we have strong acids, we're going to see we have weak bases, and then we're going to see some examples of strong bases are kind of already a category that we've seen on the IC side. But so let's talk about acids first in a little bit more detail than previously. So we see a few examples here of like HCl, HNO3, H2SO4, acetic acid. We know how to name a lot of acids, so hopefully we can recognize a lot of different compounds that have the word acid listed with them. So we can, if you think of how many acids you know how to name, probably like 20, 25 acids from the nomenclature topic we can recognize. 7 of those are strong acids, meaning they completely dissociate in water. So there are 7 inorganic strong acids. Those would include HCl, HBr, HI, so hydrochloric, hydrobromic, hydroiodic acid, HNO3, HClO3, HClO4, so nitric, chloric, perchloric, and then the first hydrogen coming off of H2SO4. We'll talk about what we mean by first H in a minute. But these are the 7 inorganic compounds that are strong acids in water. Now, when you get to organic chemistry, you're going to learn there's a lot of organic strong there's a lot of organic strong acids that we're not going to talk about. In OChem, you can talk about those compounds. You can also talk about acid behavior in different types of solvent. We're just exclusively talking about water here in this chapter. And so the implication would be you take any of these compounds that are strong, take HCl, throw it into water. You can actually buy HCl as a gas. It's a hazardous gas, not real safe to work with, but if you bubble it through water, a lot of it will stick in the water because it's ionizing to form these ions, H plus and Cl minus. We could sometimes write, and sometimes you'll see H plus here written as H3O plus, We named it as hydronium. So you can actually kind of think about an H plus dissolved by water here, or you can leave the water out of the equation. I tend not to write hydronium as H3O plus. I tend to just write it as H plus AQ, but it's just an H plus ion surrounded by water. The chloride ion surrounded by water too, that's the whole process of ionization, is that the chloride ion has like a little water sphere. So H plus gets its own little water sphere too. And so all of these acids here would do this kind of step here. Let's think also about H2SO4, since it's the only, we'll see the word on the next slide, but diprotic means it has two H pluses that can fall off of the sulfate ion. And so only the first step is strong, meaning only the first hydrogen comes off completely in water to H plus and HSO4 minus. And then that second hydrogen is going to stay kind of attached most of the time. So we're going to see HSO4 minus is what we call a weak acid, meaning we get partial dissociation. So the HSO4 minus, anytime we have a partial reaction, we'll write an equilibrium arrow to imply that we always have some of the reactant still the HSO4 minus. So the second H plus just doesn't come off 100% of the time in solution for sulfuric acid. And so this step here occurs to about maybe 5 to 10% yield, depending on a few different details, but meaning it's not a 100% yielding reaction. But the first step, the implication is it's 100% yield. So we get complete conversion into H plus and hydrogen sulfate ion, and just like an incomplete reaction to the second H plus falling off, and then the SO4 2 minus ion. So then one other detail here to point out is, or a few other details to point out. Notice HF's not on the strong acid list. So we have 3 of the 4 common halogen acids. So we see chloride, bromide, iodide, but not HF. So notice HF's not a strong acid. Don't take that to mean HF's safe to work with. I would actually rather work with HCl, Br, or I over HF. So don't think just because something's a weak acid means it's safer to work with than a strong acid. HF's incredibly hazardous to work with. Examples of weak acid can include things like that. HF, the implication for HF is that you get partial dissociation into H plus F minus. So the fluoride likes to keep the H plus, but if you give it a second option, it'll take the second option. That second option is your DNA, and it wrecks your nervous system like really quickly. So very hazardous.
Excuse me, how is the H2SO4, how is that a strong electrolyte when it partially dissociates?
Oh, so what I would say, as long as you're getting 100% yielding of some ion, so H2SO4, you get 100% conversion into H plus and HSO4 minus. So because you get that ionization, we call it a strong electrolyte. And that's a good topic to bring up, is that the strong acids are strong electrolytes because we're getting, they're converting to ions in solution. So we would call the strong acids strong electrolytes. So you did kind of remind me to talk about the strong electrolyte word here that I didn't mention previously. So the strong acids are strong electrolytes because they're dissociating to give ions. H2SO4 is still on the list because you're getting conversion into at least the H plus and the HSO4 minus. So you're getting complete ionization. You're just not getting maybe the total ionization you would have expected if the second H fell off completely. So we could have gotten a total of 3 ions per mole of H2SO4, but we at least get 2. So think of a compound giving you at least 2 ions, a plus and a minus ion, to be called a strong electrolyte. So getting partial HF, now think of your weak acids as probably being in that like 5 to 10% yielding reaction, could be a little bit less. But our weak acids, we're not going to get anywhere near 100% ionization. And so if this reaction is only taking place about 5% yield, then we don't have very many ions in solution, not as many as we would have for like an HCl solution. So if you have a mole of HCl in water, like let's say you have a mole of HCl in a liter of water, you have 2 moles of ions in the solution. If you have a mole of HF in solution and it's only dissociating to 5% of the time, then we have about 0.1 moles per liter of solution. So we have a lot less ions in the solution when we have HF. We'll talk about molarity units and concentration units when we get maybe into Friday's lecture. So we can quantify some quantitative aspects of solution concentration, but you can sort of imagine fewer ions in solution when you have a weak electrolyte. So what are some other examples of weak acids, weak electrolytes? basically every other acid you know how to name, like nitrous acid, acetic acid, phosphoric acid, sulfurous acid, and then also that HSO4 minus ion we could say is a weak acid, but we're getting that partial reaction for that HSO4 minus ion. So this ion here, weak acid. Now, you can't really just have HSO4 minus by itself. You have to have it paired up with something. So like if you imagine having like potassium hydrogen sulfate, KHSO4, that thing's a strong electrolyte. So it doesn't make much sense to discuss the electrolytic behavior of something that's already an ion, because it would just give you more ions if it further dissociated. For the things that are neutral, when you have a neutral molecule, you can call it an electrolyte. When it's already an ion, you don't have to worry about calling it even greater or lesser forms of electrolytes than it already is. So we have weak electrolytes in the case of all of the things except for HSO4 minus. So if we're thinking of H2SO3, H2SO3 is a weak electrolyte. I wrote a 4, meant to write a 3. H2SO3 is a weak electrolyte, weak acid. So weak acid, weak electrolyte. Get partial dissociation into H plus and HSO3 minus, and then probably a very tiny extent of the HSO3 minus dissociates to the second H plus the SO3 2 minus ion. So you can imagine if we're getting less than 5% yield on the first H plus falling off, we're going to get a very tiny yield of that second H plus falling off in solution. How many of you guys had AP chemistry in high school? Anybody? If you had AP, maybe if you had a really good just ordinary high school chemistry, you may have gone through and solved equilibrium problems and kind of worked out what's the concentration of HSO4 minus. We could give you acid dissociation constants like Ka1s, Ka2s, and you can work out the concentrations of these things. That comes up in chapter 16. So if you're wondering, do we have to quantify what the concentrations are of these things? Not yet, that's a Chem 1220 topic. What we want to do here is just try to identify, well, what is a strong acid? It's one of the 7. We just have to memorize the 7 strong acids. We then have to think if we know something's an acid and it's not one of the 7 strong, the implication is that it's a weak acid. And then hopefully what we can then do is start to recognize things that aren't those strong acids but maybe look like them, that they're not going to be any type of acid. And we'll even see when we get into the base category, there's really just going to be one prototype that's a base, that's NH3. So if we're kind of noticing compounds like methane, that's not an acid or base. Water turns out not to, and we looked at this last time, if you remember, we looked at water, didn't light up the light bulb at all. So water is not any type of electrolyte. Might ionize a tiny, tiny fraction, but we're not thinking about calling it a strong electrolyte or an acid or a base. Methanol, you can see like the hydroxyl group, CH3 hydroxyl, you might think, does that release the OH minus ion in water? It doesn't. Does methanol release H plus into water? If it did, we probably would have called it something acid. If you don't see the word acid in the name, probably not an acid. And so I just want us to be able to start recognizing things that are alcohols, things that are water, things that look like hydrocarbons, that these things are not acids or bases in water. If they were, we would have like discussed those properties. So we also want to infer some properties of things that aren't on the list of being acids or bases of not being acids or bases. So if we're thinking, what's something that dissociates in water? It's going to be something that's an ionic compound or something that's a molecular compound, but where the molecular compound is something like one of these acids. We can also have the category where they're bases. We'll talk about those in the next slide or two from here. But let's recognize a few other terms we can give acids. We can talk about monoprotic acids, where we have one H plus that can be released into the solution. And we'll call something monoprotic, whether it's weak or strong. So HF's a monoprotic acid. We could call it a monoprotic weak acid. HCl is a monoprotic strong acid, but they're all still monoprotic, meaning they have one H plus that's capable of being donated into a solution. A diprotic acid is one that has 2 H pluses that can be released into the solution. So carbonic acid is an example. Sulfuric acid is an example. So notice again, it could be a weak acid still. Carbonic's a weak acid, not one of the 7 strong. And so, but we have 2 H pluses that can be released into the solution. Triprotics could look like H3PO4. I have 3 H pluses I can see there being released. Think about losing the H pluses that lead to an ion you know how to name. So if I were to write acetic acid, and say for acetic acid, is this monoprotic, diprotic, triprotic, quateroprotic, whatever 4-protic would be? You might be thinking, well, what about 4? Because I see 4 hydrogens. Well, these are not acidic hydrogens. How do you know they're not acidic? Well, if they were, we probably would have had to change the formula for this thing so we could learn how to name those things if we had lost the H pluses. You know, it's kind of like, do you know how to name the thing absent those hydrogens? The only thing we know how to name is if we lose this one H plus. If we lose that one H plus, we get acetate. If we lose any more H pluses, we don't know how to name the thing. So we start to think about recognizing an anion, remove all the H pluses. Those are the number of H pluses that can be removed from the compound. So acetic acid's monoprotic. And you can see this with citric acid, because citric acid has a lot of hydrogens, but only certain ones are acidic. And it turns out that it's that COOH group, that this is an acidic functional group in organic chemistry, where this group here is acidic, but then the alcohols, remember we talked about alcohols not being acidic, and then these are like hydrocarbon hydrogens, those aren't acidic. So these here are not acidic. So they're not falling off in solution at any point. There's no way I can just add base or do something to those solutions to get those H pluses to fall off. The only acidic hydrogens are these 3 here. So citric acid is this molecule that we're depicting here, and it turns out to be a triprotic acid. And so if we start to recognize the COOH group as an acidic group, it's what we call a functional group in organic chemistry. It's like a group we can recognize that there's some acidity there because I can release that H plus into solution. You'll talk a little bit about structurally why that's so important to have this, the carbon, oxygen, oxygen, hydrogen. If you have seen the structure, it looks like this in terms of a formula, and then you lose the hydrogen, you get the carboxylate ion. So in terms of the structure function, you talk about that a little bit at the very end of chapter 16. So you'll see why it is, but what I want us to see here is that alcohols aren't particularly acidic. If they were, we'd be talking about it right now. And then hydrocarbons aren't particularly acidic. And again, if they were, we'd be talking about it right now. Okay, so let's, the opposite of an acid, or the relationship to acids would be with bases. And so let's identify weak and strong bases. The slide's called strong, but the slide should say strong and weak bases. The first category is, well, what would a strong base be? If an acid's H plus, and if you think of water minus H plus, that would leave behind hydroxide ion. So things that make hydroxide ion are bases. So anything that increases the concentration of the hydroxide ion in water is something that we call a base. I should put the charge in the bracket. So anything that increases the concentration of hydroxide in water is termed to be a base. If we get a complete formation of hydroxide ion from a compound, it would be a strong base. So water-soluble ionic compounds that contain hydroxide ion fit the category of being compounds that would completely dissociate in water, like sodium hydroxide as a solid. Add this to water. We're, of course, going to ionize the sodium and ionize the hydroxide ion. And so because we're forming this here, allows us to call sodium hydroxide a base. Because we're getting complete 100% formation into the hydroxide ion, allows us to call sodium hydroxide a strong base. And so any of our water soluble, and of course we could have changed this to AQ here if this makes it a little less confusing, just to make sure that I was kind of thinking of taking solid, adding it to water. If we did that, it is AQ. So just to not write NaCl or NaOH solid to make you confused on if that meant it was insoluble, because we had said before writing that solid meant it was insoluble. It's definitely water soluble, because that's the point. Our water soluble ionic compounds containing hydroxide ion are strong bases. So one of the keys is for our strong bases that they're ionic compounds. You know, so strong bases are in the category of compound of being ionic compounds. Strong acids like HCl, HBr, HI, those are in the category of being molecular compounds. Now remember, the difference between NaCl and HCl is about 800 degrees C in terms of melting point. Big difference between an ionic compound versus a molecular compound. So HCl, strong acid, strong electrolyte, but molecular compound. So molecular compounds have weaker forces that hold them together, therefore have really low melting points and boiling points. HCl's boiling point's well below room temperature. It's a gas at room temperature. NaCl, having the plus minus built in, allows it to have that array of ions that it's attracted to. And so for NaOH, this is an ionic compound, not a molecular compound. It's a completely different set of properties from something like HCl. But also in terms of property or category of compounds, it's on that IC side. Okay, and so then what about weak bases? What are things that partially react with water? The best example we have for this class is ammonia, because this thing here reacts with water, and it's this nitrogen like lone pair that allows it to take that H plus from water. If I were to write water like this, H bonded to hydroxyl group, it takes the H plus, leaves behind the OH minus ion. So here this forms NH4 plus as ammonium, leaves behind hydroxide ion on water, and then this just occurs in one of those partial reactions. So let me write the equilibrium arrow to imply that we're not getting 100% reaction. So we're getting some formation of hydroxide ion, just not 100% reaction leading to hydroxide ion. So we still have a lot of ammonia that would be unreacted in water, and so we'd only have a small formation of hydroxide ion. And so the implication here is that NH3 is a weak base, weak electrolyte, because we're getting some ions, but not totally all the ions we would expect. We'd expect to get at least 2 moles of ion per mole of NH3. We're getting less than 2, is the implication. Imagine this reaction takes place to 10% yield. We'd only be getting 0.2 moles of ions for every 1 mole of NH3. So we're not getting anywhere near the ions we need to get to call NH3 a strong electrolyte. So that's why we call this a weak base, weak electrolyte. And then the only other category, this becomes hard for you guys to picture without knowing a lot of Lewis structures yet. If you have nitrogen with 3 things attached to it, where you still have a lone pair on nitrogen, we'd also call that a weak base. But these are going to be hard for us to give you formulas of where you can actually sketch and know if that nitrogen has that lone pair and what its structure looks like. So just know that you need this lone pair. So NH3 is a weak base, but NH4 is not a weak base. It's not just nitrogen being present with hydrogens, it's specifically that lone pair. So NH4 plus actually turns out to be a weak acid. Nothing to be too concerned about. I don't think we necessarily ask is NH3 a weak acid, but this might help later on in Chem 1220. If you start to get the idea that if NH3 partially reacts with water to give ammonium, then ammonium probably in water will release some H plus ions. If you have like ammonium chloride, it's going to dissolve a small amount of H plus ions. And so the conjugate, if you will, of a weak base is a weak acid. Nothing you'll probably get tested on, but that may just be a lingo if you start thinking about it now, that if you can take something weak, you're going to make an acid that's also weak. And so that's just something to maybe keep in mind for later. Okay, so then let's start thinking about how acids and bases will start to react together. But before we get there, let's just try to come up with like a way we can classify all the compounds we've kind of discussed so far. This is a chart from the book. I think this is actually a pretty confusing chart because it says, this chart's here for classifying the electrolyte behavior for water-soluble compounds. So know that this chart's already kind of addressing the compound as being water-soluble. If it's insoluble, it's not being considered on this chart. So in other words, if you have an ionic compound that's water-soluble, only category it can be in is the strong electrolyte category. There's no examples of weak electrolytes or non-electrolytes that are ionic compounds. The only other category you might have is insoluble, and if it's insoluble, it's on any kind of electrolyte. So we can't classify the electrolytic behavior as something insoluble. Okay? And so then in the case of molecular compounds, we don't necessarily go through predicting solubility per se. Like we're never going to show you a formula of some kind of alcohol. Like if I said butanol, remember butanol would be CH3, CH2, CH2, CH2 hydroxyl group. So this is butanol. I would never ask you if this is water soluble. I mean, I don't even know if it is. But if it is it a strong acid or is it a weak acid? Is it a weak base? The answer is, well, it's not named something acid. And the other implication would be that it's not something we recognize with nitrogen with a lone pair, so it's not a weak base. So it's not any kind of acid, not any kind of base. If it is water soluble, it's over in this category here being a non-electrolyte. So all the things that aren't weak acids, weak bases, or strong acids are in the category of being non-electrolytes, not ionizing at all in water. So if this thing dissolves in water, it's not going to be ionized is the point. For molecular compounds, we can have strong acids, those are strong electrolytes. We can have weak acids, weak bases, those are in the category of weak electrolytes. Now you might be thinking, well, where are the strong bases? Why are they not listed on this chart? It's because they're already here. So this includes the strong bases. Because remember, the strong bases, strong electrolytes, these were ionic compounds. So we're just looking at strong bases as being the compounds that release hydroxide ion. Those are already ionic. Those are just the water-soluble ICs containing hydroxide ion. So molecular compounds, the idea for a molecular compound would be, is it an acid or base? If it's an acid, is it strong? Strong electrolyte if so. Is it a weak acid? Weak electrolyte if so. Is it ammonia? Then it's a weak base. Does it look like ammonia? Probably won't see too many extensions of what ammonia-like molecules look like, but if it looks something like nitrogen with 3, say, methyl groups, this thing here would have a lone pair of nitrogen, this would be a weak base. So again, I'm not going to get too complicated with molecules that look like NH3 that also are weak bases. So then what we can then do is say, well, acids and bases, the idea would be that they can react together in a way kind of like precipitation reactions, except we're not going to get a precipitate here. We're going to get the acid-base reaction. Acids and bases will react to form a salt or ionic compound, but then water. And then water becomes the driving force here, because water is the thing that if we form it, it doesn't ionize back into ions, and it's kind of like the purpose the precipitate had in the precipitation reaction. So HCl with KOH, the reaction here would produce our salt, KCl. So we're just swapping the chloride and hydroxide ion, and then we would get water as the other product. So H plus and hydroxide yield water, and then water doesn't go backwards, doesn't dissociate into its ions. And so what we could be writing here is we could be, HCl is a strong acid, right? Strong electrolyte. So if we want to write a full ionic reaction, we're writing H plus chloride ion. And then KOH is a strong electrolyte. It's an ionic compound. It's also a strong base. So this is a strong acid plus a strong base. And then the ion would be K plus and hydroxide ion. KCl is the salt ionic compound, water soluble. So this would be K plus and chloride ion. And then H2O, is this a strong electrolyte? No, of course not. Water doesn't fully dissociate. Water barely dissociates. Less than 10 to the minus 5% of water is ever dissociated in H plus and OH minus ions. That's more of a Chem 1220 topic though. But water liquid stays intact as water liquid. So this is the driving force like the precipitate was that allows an actual reaction to take place. So I have a net reaction taking place. I can cancel out my spectator still. So K plus chloride ion are the spectators. Again, they watch the reaction. They're there for it. They don't just disappear, but they can be balanced out of the net change. The net change would be H plus AQ plus hydroxide ion AQ goes to water liquid. I could have written the AQs in here, and I probably should have, but it just kind of makes that reaction look a lot more complicated because it's like H plus AQ, Cl minus AQ. So we could write the AQs in the full ionic equation, just clutters it up a little bit. So I like to include them when I write the balanced net ionic, just to try to neaten up the net ionic a little bit to be a little bit more precise. They have the ions coming together to form the non-electrolyte water. If you want to call water a weak electrolyte, that's fine too. I don't know. That's maybe not that big of a deal. But for water, I like to think of it as not really ionizing to a large enough extent that we call it any type of acid or base. So it's not fitting the category of being any type of electrolyte. Okay, so this is the net ionic equation. We can see net reaction for forming water. We can do the same thing for like a weak acid. It looks almost the same when we balance out HF, but just remember HF's a weak acid, weak electrolyte. It's not like the other hydrohalic strong acids. And so, but we still get the formation of the same product. So a weak acid can react with a strong base. We get the same products. We get this also to 100% yield. You might be wondering, does the weak acid react with the strong acid less effectively or less much? No, it reacts 100% still. And so we get 100% reaction here. Anytime I don't get 100% reaction, I'm going to show an equilibrium arrow. So I don't get one of those equilibrium arrows here. I get complete formation. This is why we would still call HF a monoprotic acid, because it's going to lose that H plus if given an option like a strong base to take the H plus off of the fluoride ion. And so now when I'm writing my reaction, though, I only want to dissociate the strong electrolytes. I don't want to dissociate into my ionic equation the weak electrolytes or the non-electrolytes, because they're not really dissociated fully in solution. So just try to think, what does a solution of HF look like? It looks like mostly HF and a little bit of H plus and F minus. I'm only going to write H plus and F minus if 100% of the ions would be dissociated in that solution. So HF really looks probably more like HFAQ than it does H plus or F minus AQ. So I'll leave those intact. Then I can write K plus hydroxide ion. I'll throw the AQs in there. Then we get K plus AQ plus F minus AQ. And then water liquid still, because water's still not a strong electrolyte. So I only dissociate in the reaction the strong electrolytes. So only dissociate the strong electrolytes. Don't dissociate the weak electrolytes. Don't dissociate the non-electrolytes. Don't dissociate insoluble compounds. And so then my net change here, I actually just have one spectator ion. So the only spectator ion here is potassium ion, because fluoride is still stuck onto HF in the reaction. So my net ionic is just the reaction of HFAQ plus hydroxide ion. Aqueous goes to F minus, aqueous plus water liquid. And now the reason why maybe you care about writing net ionic equations is because it allows you to address the question, is there an actual net change? Is there a net reaction? There is. It's like the way we kind of double check that a reaction is actually taking place when we mix these compounds together. Just like when we mixed whatever it was, magnesium nitrate and sodium chloride, and there was only the formation of AQs, there was no actual reaction taking place. So trying to write the net ionic is how we just verify that there's actually a net change taking place during the course of the reaction. We can do the same for, what if it's triprotic, like H3PO4? How does this reaction change? Well, it doesn't really change much at all. You could think about one KOH could take one H plus off, a second could take the second, a third KOH could take the third. But the way I like to think of this is all three of these H pluses can fall off, so I can add 3 KOHs to take each of those H pluses. And so I'm going to have 3 hydroxide ions that form 3 waters. So I'm going to have 3 H plus 3 OH minus ions pair together from H3PO4. And then that's going to leave behind PO4 3 minus. And then it's going to pair up with potassium, which is a plus, so I'm going to need 3 of them to be my salt. So in other words, if I can see that I have a triprotic acid, then all 3 of those H pluses can fall off if I add potassium hydroxide, a strong base. So I have a strong base, weak acid, we can get complete reaction all the way down to that ion I know how to name phosphate ion. So we can get all 3 of the H pluses to fall off here. So the complete reaction would be the formation of K3PO4, 3 waters. If I wanted to try to write the net ionic equation, the net change, again, I don't dissociate phosphoric acid because it's not a strong electrolyte. KOH is a strong electrolyte, so I get K plus AQ, hydroxide ion AQ, forming 3 K pluses and phosphate ion, water-soluble ionic compound. 3 waters stay intact. So my net ionic equation, again, only potassium is a spectator, and so that would be my net ionic. I'll just imagine K plus being neglected. That's our net ionic equation, would be H3PO4AQ, plus I forgot the 3 hydroxide ions from the 3 KOHs, so 3 hydroxide ions, then react with that to form PO4 3 minus and 3 waters. So that's our net change when we have the reaction between a weak acid and a strong base. But where the weak acid's triprotic, we just get all the triprotic, all the 3 H pluses falling off in that strong base. Then we can also have a weak base react with the strong acid. What are we going to form here? Well, ammonia takes the H plus, so we form NH4Cl. That's a water-soluble compound from our solubility chart. And so our net ionic would be H plus Cl minus plus NH3 goes to NH4 plus chloride. So only chlorides are spectator. So our net ionic is just H plus ammonia goes to ammonium. So our net ionic is just these ions here, all of them being AQ, forming together to form ammonium cation. So we can write these reactions for our weak acid, our strong acid, weak base reactions. So as long as one of the two is strong, you can have bases and acids react together, just at least one of them has to be strong. Strong acid, weak base, strong acid, strong base, or if you have a weak acid, just need a strong base. All right, we'll pick up a couple other reactions next time and then get into section 4.4. All right, guys, have a great day.